Hi and welcome. This time around I thought I'd try something new, much like this camera work. I thought I'd try some friction welding. I've seen it on several YouTube channels, mostly in heavy manufacturing. I saw a drive shaft put on a coupling before with friction welding and a couple similar items to that. And the whole idea fascinates me, just friction generating enough heat to cause materials to get hot and weld together. I would assume that at the interface there would be very little oxygen there, so you wouldn't have to worry about as much oxidation. Maybe that's not the case, I'm not very sure. I've got three pieces of material here that I thought I'd possibly give a shot with. 6061 aluminum, some form of brass, and common grade of titanium potentially. I'm also going to look for some regular steel. I'm not sure I'm going to do the titanium because it may just oxidize too fast. I'm really curious about that, so maybe I will. Anyways, we're gonna give these guys a shot and see if we can pull off some friction welding on the lathe behind me right there. So I've thought about solutions for pulling this off, and the standard methodology is you hold it in the tail. You hold one part in the tailstock. This is an ER40 collet chuck that fits in my MT4 tailstock. You could also use a large drill chuck to hold the part. So what that gives you is the ability to hold the part fixed and sturdily in the tailstock, and then you've got the other side, the other part in the moving chuck. This is the part that's going to be generating all the friction because it'll be rotating. Now, once these parts get, one's spinning, one's fixed, and you're pressing them against each other really hard, once they get really hot and it starts to turn plastic and then liquid, you want to be able to stop it so that the two parts can stay welded together, right? Because if one is moving and the other stopped, they're never going to weld together until they both come to the same speed, so that relative to each other, they're stopped. So one solution on my lathe is to use the emergency brake here, which applies a disc brake to the motor. And that would stop the motor, which goes through the belts and the whole drivetrain, all the gears, and finally potentially this very large 60-pound six-jaw chuck, and would stop very quickly. But all that force, all the momentum of this very heavy chuck would be transferred through the gear train, all of the way to the gear train being transferred down the belt. None of that seems like a good idea to me to stop quickly. There's a lot of forces at play here. I could potentially break a tooth, just create an unnecessary wear. It's hard on the bearings. So I don't know if that's the best solution. Another thought I had was to make a quick release on the tailstock. So this side's moving, this side's fixed. Make a quick release that would let the tailstock, the part where the part's mounted, just spin freely at some point by flipping a lever. That's somewhat complicated, and I thought about that for a while. And something like a pin between two parts, there's gonna be enough force that may not be an easy release method. So I don't know that that's a good solution. So I've moved on to yet another idea, and this one I think might be more elegant. Get rid of the big heavy chuck for starters. We don't need it here. We're gonna try the 5C collet chuck that I made before, right here. The 5C collet chuck has the part that fits in the MT6 spindle where the 5C collet gets mounted. And what I could do is, when this thing gets up to speed, gets really hot, starts to turn liquid, I pull the lever and back, it pops the 5C collet out, makes it loose, allows the part to rotate freely inside, and then I can hit the brake after when there's no load on the system and stop it there, and let's see if that works. That seems to be a very simple and elegant solution, so we're going to try that one first. If you're wondering about the brake in my lathe, if we come down here to the motor, you'll see there is a shaft off to the right that attaches to the foot pedal, and then the shaft rotates an arm that pulls on a strap going around a pulley on the motor with friction material on it. So when you step on the emergency brake, it disengages the motor electronically and pulls the strap tight around the pulley and stops the motor. Now, I was thinking about doing the same design for the tailstock, and I'll do that if it doesn't work. But for now, we're going to try hopefully the simpler design with the collet puller and see if that works just as well. Trying to decide on shaft length for these guys, you'll notice that these collets have an engagement zone of about 1 inch inside. They vary from collet to collet. This is a hard hinge collet. This is another one. This one, the engagement is most of the length, and boy, is that filthy inside. I need to clean that. Here is a more clear-cut example of the engagement zone. You can see it goes down an inch and then tapers in immediately for the rest of the length. So we're going to go back about an inch. We're going to take these guys down to 3/4 of an inch. That'll put a nice lip around the edge here. And if you had a hard time imagining before, what I want is the 1-inch diameter material to sit against the peak here of the 3/4 inch collet so that it can't push back into the collet. So that's why we're making the shaft. Otherwise, I could just use the 1-inch collet and do the whole thing. Although I got to say, all this material is a little bit tight on the 1-inch. We're going to shoot for a couple thousandths under 750. That way it will be sloppy in the collet when I release it, which is what I want. Demonstrate the fit I was looking for. This is a 3/4 inch collet and I wanted it. This collet's obviously undersized a bit. I mean, when you start tightening it, it's obviously going to get closer, but I wanted it to be able to spin freely because that's what I intend on doing. So it's 1.2 thousandths undersized, and here's 3/4 collet. And the aluminum. And the titanium. I'm going to take smaller bites with the titanium because it's a nasty material to work with. We're going to do 50 thousandths passes. Got to be careful with titanium not to let too many chips accumulate in the tray, because if you get a fire, you're going to be unhappy. You damage your lathe. I'm getting ready to prepare the other sides here. I cut this one shorter so it wouldn't stick out as much, although I realize I got a problem because I really don't want to cut this big chunk of titanium down because it'll make a piece that's too small to use. So I'm going to try and leave it long, which may be a problem. The other thing that I recognize that may end up being a serious problem is that the melting point differential between the materials, if it's too high, they're not going to weld together properly because one will turn to liquid before the other one has started to melt, even gotten plastic. So this titanium may completely fail. I think, I got to go look it up, but I think brass and aluminum are closer together. I did arrive at one disturbing conclusion while I started thinking about this. So I was looking at the relative melting points, and they're quite a distance apart from each other. Even brass and aluminum are a couple hundred Celsius apart. Titanium is much higher melting point. And then I thought, what am I going to do with the titanium when it starts to melt and becomes highly reactive in the atmosphere? It may be too dangerous to do. I've still got to reconsider that. I may have to skip the titanium. The brass is also kind of expensive, so I'm going to leave it long as well. All right, here's my setup. I have the aluminum in the quick release collet puller, and I have the brass in an ER40 MT4 tailstock, and I've got these guys as close together as I can. What I'm going to do is I'm going to start this guy up. I'm going to push them into each other at high RPM. I'm going to stay well away from all of it. I've got a welding blanket underneath it, and then when I think they've gotten hot enough to melt, I'm going to pull the collet puller and then stop the lathe. And when I pull the collet puller, it should release the aluminum slug to spin freely, and then hopefully it'll stay welded to the brass. We'll just have to see. Before I start this, I recognize what I'm doing is extremely dangerous. There are a ton of forces involved here and potentially molten metal, and so it could be catastrophic. So don't do this at home. Well, first go did not work so well. Looks like it started to melt. I think what's happening is there's so much force, I'm going to have to release the hand wheel on the tailstock because it's also pushing against the face of the collet, which didn't let it run freely. So we're going to try it again. This still may not work, but it's an interesting experiment. Nope. I'm going to put it forward of it, see if what happens there. No, they wouldn't stick. I can see the brass starting to mushroom. Yeah, the brass mushroomed quite a bit, but it did not, alas, it did not work. So it looks like the brass either wore or melted. Look at that. The aluminum is pretty much flat and not anywhere near as hot. You can see some of the brass starting to stick to the aluminum there. Pretty bizarre. I think I need to reface the brass piece and try again. All right, once again, we've cleaned up the brass and the aluminum, made nice flat faces for them. And you can tell the temperature changed the grain structure a little bit across the face. That's pretty amazing. So we were going 1100 RPM. We're going to drop down to 440. Nope. You can hear it sticking a little bit at the end there as it comes to a stop, but alas, it did not. Just scored up the brass, something fierce. Yeah, see again, there's some welding of brass on the aluminum. You can see that there. I think possibly one of the problems is the temperature differential between the two materials is enough. It's a couple hundred Celsius that if you don't reach your temperature really fast on the high one, and the low one's already turning to a liquid, it's deforming, and also these are really good heat sinking materials, especially the aluminum. I'm a little disappointed by this. Okay, so maybe it's the differential melting points that causes the brass to melt first and smear onto the aluminum. So making the two of them stick together is a bit challenging. So we are going to try brass on brass, the same melting point. Maybe that'll be easier. Nope. Maybe I'm just not going long enough either, is the other possibility. Nope. Nope, that didn't work either. Did melt some brass, and then the chunk of molten brass spun around inside. I'll show you. So there again, big chunk of molten brass was spinning around. It's welded on pretty good. The other side just had a groove cut out of it once the brass melted. Interesting thing is you would think that the hottest part would be the outside, so the melting would happen there. But it looks like it's come out of the inside instead, which is curious. Against my better judgment, I'm going to try the titanium. I don't think that's going to work either, especially since it's got a much higher melting point. But maybe it'll get hot enough that it'll get plastic, because there is aluminum in this titanium alloy, so maybe at some point at the edge boundary they will stick. I kind of doubt it. Space it out a little bit. Okay, I stopped everything all at once. Ooh, look. Holy cow. I got some welding. I had to use the foot brake to do that. It had to happen very abruptly. The free spinning idea did not work. Wow, okay. Oops. That was some welding though. Look at that. Not a very strong weld. Well, I think maybe we will try this with aluminum and brass again. Ow, so hot, so hot. But the titanium actually worked really well. That's actually melted there. All right, we've refaced the parts. I think we're going to try and do a aluminum to brass again, except this time use the brake, even though I don't like doing it because it's hard on the machine, but seems like that's a much better solution. Nope, no luck welding there. As usual, a little chunk of brass came off on the aluminum. So the brass does weld the aluminum, just not work well enough. Not quite sure what the problem is. Let's go back to titanium. One more time with titanium and aluminum. Well, let's see, did we? Hey, look at that. Looks like we got welding again. So I'm having much better luck with titanium and aluminum than I did with brass in any case. I'm really surprised that the titanium aluminum, because the titanium has a much, much higher melting point than aluminum. So I'm surprised. Oh, this time it's on, ouch, it's on there. Holy cow, that's hot. The aluminum's hot, the titanium is not. So I can't easily break it off. No, that's actually pretty sturdy. Actually got a decent weld that time between the titanium and aluminum. Oh, look at that. So you see the point where it's not wobbling there. I actually was able to get a really good finish between the two. That's actually very pretty. So as you can see here, I tried to bandsaw off the titanium. Oh, that didn't go so well. My blade's dull. Even at 120 surface feet per minute, it just dulled the blade right up. And this was like 15 minutes of cutting. So we're going to try and part it off instead. Well, unfortunately, I broke my weld, damn it. Well, that's disappointing. But the weld was actually pretty good. Couldn't leave well enough alone, so I'm trying a third time. And so I'm releasing the handle at the same time I'm stopping the lathe. And it pulls right out. That's a good sign. It welds every time, it's just not a very strong weld. And it could be simply oxide layer on the surface of titanium, oxide layer on the aluminum, preventing the weld from being very good. I actually see some pressed out aluminum this time. So maybe it's a better weld. I cleaned off the face. Last time I tried it with the oxidized aluminum still left there. That was probably a mistake too. So I'm gonna try and part this off yet again, see if I can get anywhere. I don't have high hopes. Okay, So we were able to successfully part this, and you can even see aluminum squeezed out on the inside, which is kind of cool. And it feels like they're married pretty nicely. I was going to try and turn this, but I think because of this interrupted cut, the moment I try and turn this, it's going to damage it and it's going to pop off again. Well, I'm actually able to face it this time. The weld is a lot stronger. And the combination material actually turns all right. So it's funny, use sandpaper, and the aluminum's so much softer than the titanium that the aluminum abrades much faster, and then you end up with a little lip. That's very interesting. But in the end, we were successfully able to get these two to weld together, and this is actually a decently strong weld this time. I'm kind of impressed. So there you go. Thanks for watching. Hope you find it useful. Hope to see you next time.